Algebraic Structures, Lecture 23, Ruler and Compass Constructions. Let us start with the setup. Assume that we are given a finite collection of points in R2, which we just denote by capital P. Assume that we have an unmarked ruler and a compass, so that we can draw straight lines and circles. We are allowed to draw a straight line through any two different points in our set, and we are allowed to draw a circle with a center in one of the points in our set and with the radius equal to the distance between two different points of our set. A point in R squared is elementary constructible if it is the intersection of two different lines or two different circles, or a line and a circle as above. So we can add to our set P an elementary constructible point, so we can enlarge the set and then start over with construction. The main question for today is which points in R squared can be constructed starting from our set P by the above rules in a finite number of steps. We will call such points constructible. It is obvious that the number of constructible points is countable, so it is clear that not all points in R squared are constructible. Here is an example. If we have 2 points, then we can construct the middle point of the segment between these 2 points. Here is the explicit algorithm. So let x and y be 2 different points in our set P. We can draw a straight line, which we call L1, through x and y. Next, we draw a circle C1 with center x and radius x minus y, so the distance between x and y. And then we draw a circle C2 with the center y and the same radius. The radius is the distance between x and y. The intersection of these two circles consists of 2 points, which we call u and v. And then we draw a straight line L2 through u and v. And the intersection of the line L1 and the line L2 is the point which we call Q, and this is the middle point of the segment with endpoints x and y. So here is the geometric picture. So we have our x, we have our y, we draw the straight line L1 through x and y. Now we draw a circle with the center of x and the radius, the distance between x and y, so this is our circle. Similarly, we draw a circle with center y and the same radius. And now we have 2 intersection points, u here and v here. We draw the line L2 through u and v, and now we have the point Q, and this is exactly the middle point of the segment x, y. This is how it works in practice in a very concrete example. Now let us make some elementary observations. Assume that we are given a coordinate system in R2. Then all our points in P can be described using their coordinates. The equation for a straight line is linear, and the equation for a circle is quadratic. Therefore, the coordinates of new points can be obtained from the coordinates of all points by solving a system consisting of 2 equations, each either linear or quadratic. Using substitution of variables, this reduces to solving linear and quadratic equations in one variables, starting from the coordinates of the original points. So this looks as something that can be analyzed using Galois theory, because Galois theory was about solutions of polynomial equations. Let us denote by little k the subfield of R, which is generated by the coordinates of all points in P. Assume that u is a new point that we constructed from our set P in one step by allowed method, so elementary constructible point. Let capital F be the extension of k, which is given by adjoining to k the coordinates of this point u. Then f is equal to k actually if to construct u we just needed to solve linear equations, because fields are closed under solutions of linear equations. Furthermore, either f is equal to k, or the dimension of f over k is 2, if to construct u we needed to solve quadratic equations. Which case we have depends on the quadratic equations, so sometimes solutions of quadratic equations belong to the original field, sometimes they belong to the field extension of degree 2. But now, this gives us the following consequence. So if p' is a finite set of points which we constructed in the allowed way, starting from the set P, and if capital L is the field generated by the coordinates of the points in P', then the dimension of capital A over K must be a power of 2. Because at each elementary step we either stay in the same field or we add a field extension of degree 2. So if we combine a finite number of such extensions, the total extension will be a power of 2. Great, now let us go to particular classical questions about constructions using ruler and compass. So, the first application is the problem of squaring the circle. Formulation: we start from two different points x and y in R squared, and we have the circle C with the center x and radius the distance between x and y. Problem: is it possible to construct, using ruler and compass, two points u and v such that the area of the square with the side the distance between u and v is the same as the area of the circle C? Let us note that right angles, so the angles pi over 2 or 90 degrees, are constructible, and hence, if we have such two points u and v, we can construct all other vertices of the corresponding square. That is no problem. Now, whether we can solve this problem or not. So without loss of generality, of course, we may assume that x is the origin of our coordinate system and y is the point 1, 0, because we can rescale the coordinate system. Therefore, in this case, the area of C is pi, so our circle C has area pi. And this means that we need to construct the point with coordinates the square root of pi, 0. Well, we know that pi is transcendental, so the square root of pi is transcendental as well. And so the square root of pi doesn't belong to any extension of q whose degree is a power of 2. In fact, if we adjoin to q the square root of pi, we get an extension of infinite degree. So this means that our point, square root of pi, 0, is not constructible, and so this problem is not solvable. The next problem is the problem of doubling the cube. Here is the formulation. We start from two different points x and y in R squared. And then in R cubed we have the cube q, whose edge has lengths the distance between x and y. Our problem is to construct, using ruler and compass, a point u in R squared such that the volume of the cube with the edge of the lengths the distance between u and x is twice the volume of q. Just like in the previous problem, without loss of generality, we may assume that x is the origin and y is the point 1, 0. So our field little k is just the field of rational numbers. Therefore, under this assumption, the volume of our cube q is just 1. So we need to construct a cube with volume 2, but then, of course, this means that the edge of this cube should have lengths the cubic root of 2. So we need to construct the point the cubic root of 2, 0. But the minimal polynomial of the cubic root of 2 is x cubed minus 2. And this polynomial is irreducible over q by Eisenstein's criterion, or alternatively, because it doesn't have any roots in q, by the rational root theorem. Consequence: the dimension of the field extension where we adjoin to q this cubic root of 2 is equal to 3. This is not a power of 2, and this means that our point, the cubic root of 2, 0, is not constructible. and thus the above problem is not solvable. Problem number 3 is the problem of trisecting an angle. Here is a formulation. We start from 3 different points x, y, and z in R squared. Problem: is it possible to construct, using ruler and compass, a point U in R squared such that the angle between the lines xy and uy is exactly 3 times smaller than the angle between the lines xy and zy? We claim that this problem is not solvable in general, but of course it might be solvable for some specific values of x, y, and z. So we will construct an explicit counterexample. Let us assume that x, y, and z are the vertices of the equilateral triangle. So this means that the angle between xy and zy is 60 degrees, so pi over 3. Without loss of generality, we again assume that x is the origin and the y is the point 1, 0, and then up to sign the point z will be 1/2 of 1, the square root of 3. And this means that our field k, which we start from, so the field generated by the coordinates of our points, is the extension of the rational numbers when we add to the rational numbers the square root of 3. So this is our starting field. So now 1/3 of 60 degrees is of course 20 degrees, and so we claim that the angle of 20 degrees is not constructible. Indeed, if we can construct the angle of 20 degrees, then we can construct the point U with the coordinate 0 and then the tangent of 20 degrees. That's because the angle between xy and yu is 20 degrees under the circumstances, and u belongs to the intersection of uy with the orthogonal to xy going through the point x. So if we construct an angle of 20 degrees, we should be able to construct the number tangent of 20 degrees. So let's denote by x tangent of 20 degrees, and let us use the formula for the tangent of the triple angle. So the tangent of 3 theta is equal to 3 tangent of theta minus tangent cubed of theta divided by 1 minus 3 tangent squared of theta. The tangent of 60 degrees is equal to the square root of 3, and then this means that plugging this into this formula, we get the following equation for x. X cubed minus 3 square root of 3x squared minus 3x plus the square root of 3 is equal to 0. Note that this is a polynomial equation over our field of q with the square root of 3 added. It's not a polynomial equation with rational coefficients. Our starting field is strictly bigger than q. We claim that this polynomial is irreducible over our starting field of q with the square root of 3 added. Of course, being a polynomial of degree 3, its irreducibility is equivalent to the claim that it doesn't have roots in q with the square root of 3 added. The field q with the square root of 3 added is of course a quadratic extension of q with the basis consisting of 1 and the square root of 3. And so every element in this field can be written as a plus b square root of 3, where a and b are rational numbers. So if we take such an element and we plug it in our polynomial, we get the following equation. A plus b square root of 3 cubed minus 3 square root of 3 times a plus b square root of 3 squared minus 3a plus b square root of 3 plus the square root of 3 is equal to 0. We can rewrite this in the following way, so we just compute all these cubes, squares, and we collect the rational part and the part with the factors the square root of 3 separately. So we get a cubed plus 9ab squared minus 18ab minus 3a, that's the rational part, plus 3a squared b plus 3b cubed minus 3a squared minus 9b squared minus 3b plus 1 times the square root of 3 is equal to 0. So since 1 and square root of 3 are linearly independent over q, the two coefficients must be 0. So we get the system of two equations. The first coefficient is 0 and the second coefficient is 0. Now we see that in the first equation a is a common factor. So if a is equal to 0, then of course the first equation is satisfied. But then the second equation reduces to 3b cubed minus 9b squared minus 3b plus 1 is equal to 0. Here it is very easy to check that plus minus 1 and plus minus 1/3 are not the solutions to this equation, and hence by the rational root theorem this equation doesn't have rational solutions. So there is no rational b such that a is equal to 0 and b satisfies this equation. So this is a dead end. Now if a is non-zero, then the first equation can be divided by a because it's non-zero, and then it reduces to a squared plus 9b squared minus 18b minus 3 is equal to 0. And from here we can write a squared as minus 9b squared plus 18b plus 3. And now we can plug this into the second equation, and when we compute we end up with the following equation: minus 3b cubed plus 9b squared minus 6b minus 1 is equal to 0. Here again it is easy to check that plus minus 1 and plus minus 1/3 are not the solutions, and hence by the rational root theorem this equation doesn't have rational solutions. So our system of equations is not solvable, and this means that our polynomial x cubed minus 3 square root of 3x squared minus 3x plus the square root of 3 is irreducible over the cube with the square root of 3 added. Therefore, the field extension from our starting field cube with the square root of 3 to cube with the square root of 3 and tangent of 20 degrees has degree 3, because we adjoin a root of an irreducible polynomial of degree 3. And since 3 is not a power of 2, we deduce that the point 0, the tangent of 20 degrees is not constructible. So in particular, the angle of 20 degrees is not constructible from the angle of 60 degrees. Therefore, in general, trisection of an angle is not constructible using ruler and compass. In our final application, we discuss construction of regular polygons. So here is the setup. We start with 2 points, the origin and the point y, with coordinates 1, 0 in R2. And the question is, for which positive integers n, one can construct the point un with the coordinates cos 2 pi over n and sine 2 pi over n. Let us note that if we consider the regular n-gon inscribed in the unit circle, for which our point y is one of the vertices, then the point un is exactly the next vertex of this regular n-gon if we go into the counterclockwise direction. Therefore, our question is equivalent to asking whether we can construct a regular n-gon using ruler and compass. The answer is given by the following statement, which was originally conjectured by Gauss. That's a theorem which is due to Wantzel from 1837. The point un is constructible if and only if any odd prime factor of n is square-free in n and has the form 2 to the power 2 to the power n plus 1, that is, it is a so-called Fermat prime. Let us start with some elementary observations. Elementary observation 1. All points a, 0 where a is a rational number are constructible. Proof. Recall that we start from x which is 0, 0 and y which is 1, 0. Since Q is generated by 1 as a field, we need to show that all arithmetic operations, that is addition, subtraction, multiplication and division, are constructible using ruler and compass. The addition is constructible in the following way. So if we have 2 points with distance a between them and 2 points with distance b between them, we can draw them on the same line, and then the distance between the first and the third point will be a plus b. Subtraction is constructible similarly, but we just draw those points in opposite directions. So if we have external points on the distance a, and then the points 2 and 3 in the distance b, then the distance between 1 and 2 is a minus b. Division and multiplication can be constructed using similar triangles. So we can of course construct perpendicular lines. So we draw two perpendicular lines, and then on one of them we draw the points with the distance 1 and with the distance b, and on the other one 2 points with the distance a. And then we will have on this picture, so here we have this triangle is similar to this triangle if these two lines are parallel. So using perpendicular lines we can also construct parallel lines. So if we draw the line through this point which is parallel to this line, then the distance between this point and this point will be exactly AB. And this is a way how we can multiply things using ruler and compass, and from the same picture we can always divide things. So that's our elementary observation 1. Elementary observation 2. If some un is constructible and m divides n, then um is constructible. So if n is equal to a times m, then constructing un a times, one after another, and moving in the same direction gives us That's straightforward. Observation 3. If un and are constructible, then mn divided by their greatest common divisor is also constructible. So u with the index the least common multiple of m and n is constructible. Proof. We can write the greatest common divisor as a linear combination of n and m with some integer coefficients. Now if we divide this by nm, we get that the greatest common divisor divided by nm is equal to a times 1 divided by m plus b times 1 divided by n. So now we can construct the absolute value of a times, and un, the absolute value of b times, and if a and b have the same sign, we just move in the same direction, and if they have different signs, we move in different directions, and in this way we construct exactly u with the index nm divided by n comma m. So this is our third elementary observation. Here is a consequence from this. So if we can write n as a product of powers of distinct primes, then un is constructible if and only if each u pi to the power ki is constructible. Indeed, if un is constructible, then u pi to the power ki is constructible because pi to the power ki divides n. Conversely, if each u pi to the power ki is constructible, then these pi to the power ki, they are relatively prime, and n is equal to their product. Then un is constructible by our previous observations. And observation 4, u with the index 2 to the power m is constructible for all m. That's clear because we can always divide an angle in half using ruler and compass. So dividing an angle by 2 is no problem using ruler and compass. Observation 5. If p is a prime, then the minimal polynomial of the primitive pth root of unity over rational numbers, that's the cyclotomic polynomial phi p of x, is equal to x to the power p minus 1 plus x to the power p minus 2 plus and so on plus x plus 1. We have discussed this in the previous lectures. It's clear that this polynomial annihilates the primitive pth root of unity, and to prove irreducibility, for example, one can do the variable change, substituting x by y plus 1, and then using the Eisenstein's criterion. Now let us make a more advanced observation, observation 5. If p is a prime, then the minimal polynomial of the primitive p squared roots of unity over the rational numbers is phi p squared of x. This should be p squared, which is equal to x to the power p times p minus 1 plus x to the power p times p minus 2 plus and so on all the way down to 1. This is left as an exercise, and this is a non-trivial exercise. A consequence of this, if p is an odd prime, then u with the index p squared is not constructible. Indeed, the extension from Q to q when we add the primitive p squared roots of unity, this has degree p times p minus 1 by observation 5, and this is not a power of 2 because p is an odd prime. So that's it. And now one more consequence: if p is an odd prime and up is constructible, then p is of the form 2 to the power 2 to the power m plus 1 for some m. This should be plus. Proof. The extension from q to q when we add the primitive p's root of unity, it has degree p minus 1, and it should be a power of 2. So p minus 1 should be 2 to the power r. If r has an odd divisor, say we write r is equal to a times b with a greater than 1 odd, then p, which is 2 to the power r plus 1, can be written as 2 to the power ab plus 1, and this is 1 to the power a, so this is 2 to the power b to the power a plus 1 to the power a. And then we can factor this as 2 to the power b plus 1 times 2 to the power b to the power a minus 1 minus 2 to the power b to the power a minus 2 plus, and so on, all the way down to 1. And this means that p is not a prime number, a contradiction. So, as we have seen, constructibility of un implies that n can be written as 2 to the power m times the product of distinct Fermat primes. And to complete the proof of Wantzel's theorem, we need to prove that each up where p is a Fermat prime is constructible. We will discuss this on the next slide. Let us make one funny remark. So far, only 5 Fermat primes are known: 3, 5, 17, 257, and 65,537. And that's it. Let us now discuss constructibility of regular polygons for Fermat primes. Assume that p is a Fermat prime. Then the degree of the field extension from rational numbers to rational numbers with a primitive p's root of unity added will be p minus 1, and it is a power of 2, because we assume that p is a Fermat prime. So this extension is a Galois extension, so in characteristic 0 everything is separable, and we add a root of unity, and so it splits the corresponding cyclotomic polynomial, so it's a normal extension, so it's a Galois extension. And the Galois group of this extension is a group whose order is a power of 2. And since we add a root of unity, this Galois group is abelian. And by the structure theorem of finite abelian groups, this Galois group is a product of cyclic groups. So G is a product of cyclic groups whose orders are powers of 2. Note that Z2 to the power r has an element of order 2, and this element generates a subgroup of order 2, which is isomorphic to Z2, and the quotient by this subgroup is exactly Z2 to the power r minus 1. So this means that our Galois group G has a subnormal series in which all subquotients are Z2. And this gives us, by the Galois correspondence, a flag of field extensions which start from our Q and end with Q with our primitive p's root of unity added. And in this chain of field extensions, each step has degree exactly 2. And so each step can be obtained from the previous step by solving some quadratic equation. And that's exactly what you can model using ruler and compass construction. And this implies that each up is indeed constructible. Some additional problems and questions at the end. Problem question 1. How to divide an angle in half using ruler and compass. Problem question 2. Describe in detail how to solve quadratic equations using ruler and compass. Problem question 3. Fill in all the details in the argument on the last 2 slides. Problem question 4. Prove with all details that phi p of x is irreducible over q for prime p using Eisenstein's criterion. And problem question 5. Prove with all details that if p is a prime, then the minimal polynomial for the primitive p squared roots of unity over q is phi p squared of x, and this is equal to x to the power p times p minus 1 plus x to the power p times p minus 2 plus and so on plus 1. Thank you very much and see you next time.